Poonam Singh, a professor at NIT Rourkela, and this work was done by my student Bibekananda Panda. He is a PhD research scholar. The title is A Deep Learning Framework for Predicting Signals in OFDM NOMA with various algorithms. So this is the contents of my talk. I will discuss the system model for NOMA, and then we'll see OFDM based NOMA receiver. And then deep learning is used for channel estimation and signal detection for OFDM based NOMA. And then we'll see some of the optimizers and compare their performances. So this is the introduction to NOMA, a non-orthogonal multiple access. So my area of research is wireless communication. We have seen that in first generation FDMA was used, frequency division multiple access. In second generation of cellular phones, TDMA was used, time division multiple access. In third generation CDMA was used, that is port division multiple access. And in fourth generation we had orthogonal frequency division multiple access. So all these four generations, they have used orthogonal resources for transmitting signals of different users. But for fifth generation, NOMA is proposed, which is a non-orthogonal multiple access method, where the resources need not be orthogonal. We can transmit multiple user signal on the same frequencies, but we can differentiate them in power or coding. So this way we can increase the spectral efficiency of the system because we are using the same frequencies for transmitting different user signal. And this has many advantages. Increases the bandwidth efficiency, then reduces the latency, accuracy is better, and then the performance is also improved. In NOMA, basically in the receiver, successive interference cancellation is used. In this process, one of the signal is detected first. Normally, the users who are transmitting with more power, their signal is detected first, and it is subtracted from the total signal. And then the subsequent users' signals are detected. So this process is a bit complex because we have to detect one by one each user signal and then subtract it from the remaining signal. So that is why in recent times, deep learning based NOMA has been proposed, where deep learning methods are used for decoding the signals of multiple users at the same time. And we have used this deep learning, different algorithms and different structures of deep learning network for detecting the signals. This is the system model for, we have chosen uplink NOMA. Same thing can be done for downlink with slight variations. So if there are, say, L number of users, as we can see here, U1 to UL, all are transmitting in uplink to the base station. In this case, we can see that the positions of these users are different, and based on their distances, the powers are allocated. The user who is closest to the base station is allocated minimum power, and the user who is at the farthest distance is allocated maximum power. So this way, each user will be transmitting with different power, but at the base station, we will receive the signals with almost same power. And in then after receiving the signal, successive interference cancellation is done, where the user who is transmitting with maximum power, that is U1, its signal is detected first, and it is subtracted from the total signal. Then U2, then U3, and this way the signals are detected. We have done the analysis with two users, just to simplify the case. So this is the model that we have taken. There are two users, and one is a far user, and the one is near user, transmitting with different powers. So we can see the how the data is transmitted in that diagram. The data across the frequencies, subcarriers, and along different time slots is shown there. So different users' data can be transmitted in the same frequency band, and we can also transmit in different time slots. And these signals are passed through the deep learning network. So in the receiver, we receive this signal. The first, we pass it through deep learning network, where we have multiple layers, multiple hidden layers. Here 2 layers are shown. And then we have a fully connected layer, and then the activation layer, where ReLU is used as an activation function. then there's softmax layer, and finally the classification layer. So as I said, all the users use the same frequency resources simultaneously. So here we receive, in this case, there are two users. So in the receiver, we'll have two users data plus interference plus noise. The power distribution is carried out, assuming that both the transmitter and receiver, they have channel state information. Because if the channel is known, then we can transmit. If the channel is good, we transmit with more power. If the less power. If the channel is very bad, then we transmit with more power. So this information has to be there in the transmitter. If the transmitter knows about the channel, then only this power allocation can be done. And this channel state information can be known by estimating the channel at the receiver and then transmitting this information to the transmitter. Normally that is the process. Or it can also be done at the base station. So this power distribution gives a reasonable signal to interference plus noise ratio for each of the users. And by using, suppose we are having an OFDM system, normally in this system we have combined OFDM with NOMA. So in OFDM we have multiple orthogonal frequency subcarriers. On each subcarriers, we can transmit more than one user signal. So each subcarrier, let us say, carries L users signal. So the received signal on each subcarrier can be given by this expression 1, where the received signal is denoted by Vt, and it is summation of each user's signal, that is the power multiplied with the channel gain multiplied by the transmitted signal, plus additive noise. So this will be the received signal at each of the user. Now from this we have to detect each user's signal separately. So in deep learning method, there are different structures, like we can use either gated recurrent unit, which is this architecture is shown here. We have in this neural network, there is no output gate. So as compared to LSTM, this is slightly simplified. We have only 2 gates, and there is a reset and update one, and these are used to calculate the final output. So the outputs of the GRE block are calculated as given by this equations 2, 3, 4, 5. The Z, R, and Z and R are calculated using a sigmoid function. Sigmoid is used as activation function, and for calculating HT, tan hyperbolic function is used. The difference is in sigmoid, the output is restricted between 0 and 1, whereas in tan hyperbolic function, the output is restricted between -1 and 1. And another architecture is long short-term memory, LSTM. LSTM has this 3 stages: forget, update, and output. And the outputs are computed using this equation 6 to 11, where we see I, F, and O are computed using the sigmoid function, whereas CT, the final output, is computed using CT, cap, and HT are computed using tan hyperbolic function. So this is the basic LSTM structure, which is used by in many applications. The advantage here is this is slightly more complex, but it gives better performance as compared to the GRU. And the structure that is used commonly is Bi-LSTM. Bi-LSTM expands the LSTM model into 2 models. One is they are in different directions. As you can see, in the first case, we find the output from the input. So we can predict the outputs based on the past inputs. And in the second stage, the input can be detected based on the outputs. So this is the structure of Bi-LSTM. You can see it is bidirectional. That is the name. That is why the name is bidirectional long short term. There is something wrong. It's not. Can I use the PDF? We have used some optimization techniques, and this optimization techniques are used for updating the weights of the neural network model, deep learning model. And these weights are normally updated based on the error. So if you find the error and using that error, there are different methods for updating the weights. So one of this is root mean squared propagation, RMS prop, this method. In this case, we try to minimize the root mean square error that is propagated through the different layers. And these are the equations. Yeah, okay, this is the third one. Some of the slides are not visible properly. Okay. The first method is only the second one. The third method is adaptive momentum based algorithm, where these are the expressions. And for simulation, we have taken these parameters. Number of subcarriers we have chosen to be 64 in OFDM model. There are 2 users, and cyclic prefix used for OFDM is either 16 or 8. So it depends on the channel. If the channel is the delay spread of the channel is more, then we need a longer cyclic prefix. Training data of 3,20,000 is used, and 3 different architectures are used. That is GRU, LSTM, and Bi-LSTM. And 3 different optimizers are used: SGDM, RMS prop, and these are the simulation results. So the simulation is carried out for each of the combinations for different structures and different algorithms, and is compared with the basic structure, that is SIC, MMSE, SIC, minimum mean square error for the successive interference cancellation technique. And we see that the performance is much better than MMSE SIC if we use these deep learning techniques. And the best result we get when we use Bi-LSTM with ADAM, the blue line. And for others, the performance is slightly deteriorated, but it can be used. So depending on the application, if you want very accurate result, then we go for Bi-LSTM ADAM. Otherwise, we can slightly reduce the complexity of the receiver and go for other techniques also, like GRU, SGDM. And this was the performance for cyclic prefix of 16. And this is the performance, this is for user 1 and this is for user 2. So because we are detecting user 1 signal first, we see that the performance of user 1 is much better than user 2. Performance we can see because bit error rate we are getting here 10 to the power minus 2 at a bit SNR of 25 dB. Whereas in this case, we get at the same 25 dB, we get a bit error rate of about 10 to the power minus 6 or 10 to the power minus 5. Yes. So this is much better. And same simulation is carried out for cyclic prefix of 8. So if we reduce the size of cyclic prefix, we see the performance slightly deteriorates. Like we are getting a bit error rate of 10 to the power minus 3 at 25 dB, or 5 into 10 to the power minus 3. And similarly, for the second user also, the performance deteriorates slightly when the cyclic prefix is reduced. So these are the simulation results, and this is a comparison table for each of the methods. SIC, MMSE is the existing method, and all other methods are based on deep learning, the different algorithms and different structures. And we see the best result is given by the last one, that is ADAM algorithm with Bi-LSTM structure. So this is the conclusion. Here we have compared the BR performance of the different models, GRU, unidirectional and bidirectional LSTM with different optimizers. And it is observed that by using more training layers, we can improve the performance. And the performance of layer-based Bi-LSTM is much better than other models. So different deep learning based optimizers are also used here, and with different cyclic prefixes. And we have plans to extend it for a heterogeneous NOMA network, where different devices are using different type of algorithms, and still this can be used. And also for massive MIMO, where a large number of antennas are used for transmission and reception. So this is our future work. And these are the references. So, any questions?